Now, let's take a more detailed look at some of the components, additional information and ideas. The electromagnets and their contacts both moving towards each other is a big advantage, because an electromagnet and its contact both pull towards each other. So if either one is attached to a fixed frame and not able to move, then the energy of the fixed side pulling towards its contact is absorbed into the frame holding it in place, and therefore is lost. Allowing both the electromagnets and contacts to move towards each other uses all the kinetic energy of the magnetic attraction and not just half of it. I've avoided the use of exotic or expensive materials wherever possible, and there are no rare earth magnets in this design. Most of the main dimensions, sizes, patterns and positioning of the designed components are divisible by 3. Doing this has created a good end result with the relative sizes and positioning of things in the design. The 2 alternator generators I have chosen for this prototype are these ones. This generator head is reasonably inexpensive, costing approximately £500 each. One of these requires 24 brake horsepower to spin its axle at 1500 RPM to produce 12 kilowatts of electricity. The main drive wheels are designed with symmetry and balance in mind, so they are able to spin fast with minimal vibration. They have thin circular V-shaped grooves around the edge of the wheel, which channel the airflow and have the effect of maintaining balance and smooth spinning of the wheel. It's a technique I learned from the aerospace industry's advanced aircraft designs, where channeling the airflow along tiny grooves in a straight line has a stabilizing effect. The ring towards the outside of the front of each main wheel is a heat-resistant rubber track that the differential wheels run on for better traction to eliminate slipping and reduce wear of the differential wheel rubber tire rings. The wheel is attached to the generator axle with a steel coupling which allows the entire wheel's assembly position to be adjusted forwards or backwards a bit if necessary. The coupling and wheel fits together with a hexagonal fitting to make the joints strong enough for the turning force produced by the drive's electromagnets to turn the generator axle, which the coupling is attached to. The electromagnet passive contact can be made of soft iron, which has a strong attraction to magnets. Any other material that is attracted to magnetism can be used. The more magnetic attraction of the material used, the more the electromagnets and the contacts will pull towards each other. The electromagnets are wired so that each one has the opposite polarity of its neighbors to prevent the passive contacts from becoming magnetized, as each one is attracted by alternating positive and negative. The core of the electromagnet must be made of a material which allows the electromagnet to magnetize and demagnetize very rapidly. The electromagnet should be able to be powered by between 12 and 24 volts. The actual dimensions of the electromagnet wire windings and the core will be decided after consultation with electromagnet experts. Adjustments can be made to the switch timing to compensate for minor time delays. However, the requirement for the electromagnets to be able to switch on and off very fast are essential due to the speed at which the drive needs to run. Using iron-cobalt alloy for the electromagnet core may be ideal, as it has the highest potential magnetism known, so it magnetizes and demagnetizes very fast and powerfully. The front side of the core has a larger diameter to increase the magnetized surface area of the electromagnet for more even magnetic attraction across the front. This feature isn't essential though. The electromagnet can be wound with copper wire or whatever an electromagnetics expert would recommend in order to achieve the desired result. Using silver-infused copper wire for the electromagnet winding and other wiring would greatly increase the efficiency and reduce energy losses as it has much better conductive properties. The electromagnet's winding is covered by a heat-conducting and electrical insulating layer so that the winding wire doesn't touch the drive wheel or the electromagnet hold screws, and heat generated by the coils switching on and off is conducted into the main drive wheel. Recommended materials are either translucent epoxy from MG Chemicals or Cool Poly D-Series plastic from coolpolymers.com. The 3 reed switches used for switching the electromagnets in the active wheel turn on when in close proximity to a magnet. The reed switches used in this design are these RI64 dry reed switches because they have fast on-off switching speed, long life, and can carry the voltage required to power the electromagnets. They are also a good physical size for the design, and their operating distances and other properties work well for this application. Their normal switch state is off. Here's how I worked out how fast the reed switches would need to turn on and off. Ordinary small natural magnets are used for the switch magnets in the passive wheel, which activate the reed switches in the switching section of the active wheel. The magnets used are these small round natural magnets which are designed for magnetically activated switches. They have the right operating distances, physical size, and a hole through the center for mounting with an ordinary bolt or screw. When reed switches are turned on and off rapidly with a magnet, they spark if they are not earthed. This sparking causes a bit of current loss across the connection. Earthing the reed switch eliminates the sparking and is the usual way of dealing with this problem. The reed switch sparking can be converted to DC current using a full wave bridge rectifier instead of earthing it. This method is simply to connect the earth wire to a full wave bridge rectifier, which then converts the energy into DC current, which is then used to recharge the battery. I learned this valuable technique from Doug Conzen's YouTube video. I've used this electromagnetic shielding foil to shield the inner switching section from the magnetic fields of the main drive electromagnets. In most cases, the shielding parts in the design are 3 mm thick, but probably won't be necessary to be as thickly layered as that, depending on the effectiveness of the foil used. This material is very effective, inexpensive, easy to work with, and easily available. The rotating connector is a 4-way commutator specifically designed to fit the assembly, and its function is to facilitate electrical connections between the control box and the rotating active wheel. It may be possible to use a manufactured part for this, with a through-bore diameter of 50 mm, such as this part, but I have not been able to find one with the correct specifications, since the required connector needs to be able to run at 1500 RPM and be able to fit onto the axle in the small space and have a long working lifespan. I've opted to design a simple custom connector which allows easily changing and adjusting of the carbon brushes to facilitate this. The main disadvantage of using a one-piece manufactured slip ring connector is that the whole part would need replacing when it wears out, and it would require removing the active drive wheel and mount to do so. The custom designed rotating connector for this design is made of 2 parts. The connector ring, which is the rotating part mounted on the active generator's axle, and the connector brushes, which is the stationary part mounted on the generator front casing. The rotating connector has 4 connections to allow for a bit of flexibility with control box wiring. 2 connections will be used for positive and negative current to the reed switches and electromagnets. The other 2 connections could be used for earth and reed switch earth. The spring tension in the connector brushes, which determine how hard the brushes press against the connector rings, will need to be set in accordance with expert advice or the result of testing. Okay, let's take a closer look at the design of the differential wheels. I have used zirconia ceramic bearings in the diff wheel assemblies due to their close proximity to magnetic fields, high speeds of rotation, and better heat resistance and longer lifespan. Ceramic bearings are not significantly affected by magnetic fields, and although quite expensive, are essential for this design. The bearings used in this design are these ones. The bearings are press-fitted to the axle, and the bearing, which is the differential wheel, has a heat-resistant rubber tire ring bonded to it for traction. The 3 differential wheels have a free-floating design, each with 2 ceramic bearings. One bearing is part of the actual differential wheel, which goes between the 2 main drive wheels, and the other bearing attaches to the fixed frame. This way, the axle and 2 attached fans are completely free-floating. This will effectively reduce the RPM of the axle and fans by sharing the spin between the 2 bearings. The axle and fans should spin from the small amount of friction in the spinning bearing in the differential wheel, especially when spinning at high speeds, and cause the fan to spin fast enough to provide effective cooling for the bearings and main drive wheels. The fans are simple and can be made of any heat-resistant and reasonably strong material like plastic. They are arranged to draw air upwards between the spinning drive wheels. The drive could be cooled by other methods to be able to work in a vacuum. Here is how I worked out how fast the bearings would be spinning when the main drive is spinning at 1500 RPM. If the differential wheel arrangement had only 1 bearing without the free-floating axle, the bearing would have to spin at over 8,500 RPM, but the free-floating arrangement should reduce this significantly.